Hi, my name is Bill Fortney, and welcome back to Probability and Statistics for Engineers. In this session, we're going to get into the foundations to give you what you need to be able to answer the question, which is, as you remember, what can I expect from you? We need data to make good engineering decisions. We're asking what we can expect. If we know what we can expect, then we can get what we need in order to answer our question, whether it's a minimum, a maximum, somewhere in the middle, whatever it is. And we've seen so far that it's hard to answer what can I expect from you. Number one, because there's variation in everything. So we can't just take one reading. Since there's always variation, the one reading we may take may be a low one, and we think things are lower than they are. It might be a high one, or we think it's higher than they are. So we can't just take one reading. The other reason why it's hard is we need to know what to expect from all possible samples, not just the one sample that we have. So it's difficult. You remember the case where we were wondering whether our boss would go to jail or not. We had a sample and we had a minimum, but we realized, yeah, if I get another set of samples, then there's going to be another minimum. We need the minimum of all possible samples, and we need statistics to help us with that. Okay, now, what is statistics? It's a collection of methods for collecting, displaying, analyzing, and, important for us, drawing conclusions from data. And there's two basic types. The first type is called descriptive statistics. That's where we're describing data. The second type, which is really what we care about, is inferential. That's the type of statistics that helps drawing conclusions about a population based upon information contained in a sample from that population. And you're like, okay, those are maybe some new words, population, sample. Let me show you what I mean. Let's say we have a bag of bolts, and that bag of bolts is all we care about. When we do designs in our company, we will always use that bag of bolts. We will never use any bolts besides just that bag. So all we care about is that bag of bolts. You've heard me say that a lot. I'm emphasizing we just care about that. We have a population. We have everything that we're concerned about. So we can ask, what is your ultimate? And we can use descriptive statistics because we have everything we care about. And we can calculate what's called population parameters. We can calculate the average, the symbol is mu, the standard deviation, the symbol is sigma, and the min and the max. And in this case, the min and the max tell us everything we want to know. Like if we want to know, will our boss go to jail? Well, we can tell you because that min that we have, we will never have any min below that because we have the whole population. We have every bolt that we will ever use. Another example of that is like exam grades. You have a class. The teacher has a population. It's everyone in that class. And now if that teacher tells you the average and the standard deviation or the min and the max, you have an idea of how people did on the exam. So if the teacher tells you the average on the exam was 90 and the minimum was 85, well, then you have a really good idea that everyone did well on the exam. No one made below an 85. And on average, people were in the 90s. If they tell you that the average of the exam was 90 and the minimum was 10, well, that tells you most people did really good, but at least one person didn't do well at all on the exam. So you see, if you have the population, calculating these parameters can give you an idea of what to expect. Unfortunately, that's not the world we live in. We almost never have the population. Instead, we have to have case two where we're going to take a sample from the population. So for example, we have our factory and it's making bolts. We will never have all the bolts. We can't have all the bolts because it's continuing to produce. So we'll never have the population. In fact, when you have something like this that's producing, we typically call this a process. So when we're saying the process, that's very similar to saying, here's the population right here, the process that's producing. We can never have all of it. So what we're going to have to do is we're going to take a sample from that population. And then inferential statistics, we will use the sample from that population to try to draw conclusions about everything by studying that sample. And just like before, we can calculate some things. And this time, they're called statistics. Over on the left-hand side, if we have the population, they're called population parameters. If we're taking a sample, they're called sample statistics. They're still the same thing, but what they mean is different. So we could calculate an average. Now we use the symbol X bar. So if you use the symbol X bar, that's saying you have an average. If you calculated an average, a sample average, if you calculated the average from all the data that ever exists over here, you would use the symbol mu. Standard deviation sigma, standard deviation over here, sample is S, and we put X meaning of the X, the variable that we're taking the standard deviation of. In this case, we're going to divide by n. In this case, we're going to divide by n minus 1. And you'll see that when I show you average, the formula for standard deviation. But I just want to highlight this. Because this is a sample, there's a little bit of uncertainty. And because of statistics and all the mathematical proofs that they go through, this one needs to be divided by n minus 1. And we can get a min and a max. But, like we saw before, that min isn't the overall min. That's just the min of our sample. If we take another sample, we're going to get another min. So over here, the min and the max told us what to expect. Over here, they don't. We're just using these to estimate the population, and we're going to see that then that's going to allow us to do some statistics work in order to be able to know what to expect. Okay, so now let's say we have our factory. It's producing parts. Each of those parts, if we measured the ultimate, so x1, x2, x3, all the way up to xi, and we can record all those. Every one of those numbers that we collect, if done correctly, is called a random variable. You're like, okay, what's a random variable? A random variable is a number that varies from trial to trial, where we've seen that there's variation in everything. And it does so in a way that can't be predicted with certainty. Like I can't tell you what the next number is going to be. And you might be thinking, well, okay, but I thought this was going to help us know what to expect. It will. We can't predict where any one number will be, but random variables follow a predictable pattern described by their probability distribution. The distribution of the process, the population, the factory, generating those random variables. That's cool. They follow a predictable pattern based on their probability distribution. What's a probability distribution? A probability distribution is a mathematical function that describes the likelihood, the probability of getting different outcomes, different values from a random variable. So let me show you what I mean. First, I'm going to repeat that. Every number we collect when we take data, if it's done right, is a random variable. Random variables follow a predictable pattern based on their probability distribution. Probability distribution gives us the probability of different values happening. So one common distribution that random variables follow is the normal. So I'm going to use that as an example. Everything is not normal. You can't always just assume things are normal. We're going to work with normal first, and then we'll talk later about how do you go about knowing if it's a different distribution. So here's the normal distribution. And down here is the value that you're worried about. Okay, what is my ultimate? Up here on the y-axis, if you will, that's the probability that value will occur. And for the normal distribution, there's a formula that gives us that probability. And this is what's called a continuous distribution, which means you can have a value of 5, 5.01, 5.02. Discrete distributions, you can only have like on or off, specific values. Continuous distribution goes ever. So what we do is we would integrate this over a range of values, and it would tell us the probability of getting a value in that range. So like we could say, okay, what's the probability of getting less than this x, of more than this x, between this x and another x? So probability distributions allow us to calculate the probability of values happening. That's moving us in that right direction of being able to know what to expect from a set of data so that we can answer our engineering question. Okay, so again, I'm going to say this several times because it's new and it's important. Every number is a random variable. Those random variables follow a predictable pattern described by their distribution, and the distribution tells us the likelihood of those values happening. Okay, now a probability distribution, the predictable pattern, is described by a shape, a central tendency, and a spread. And let me show you what I mean for those on the normal. So the shape, it's a bell-shaped. So it's high in the middle, it's symmetric on either side, and then it trails down and goes out to the edge. The central tendency for a normal is right here in the middle, and it's the average of the data. The spread is determined by the standard deviation, and the spread is how far out this bell goes. If we have a really narrow bell, that's a small standard deviation. If this bell lingers way out, that's a large standard deviation. So every number we collect is a random variable, and they follow a predictable pattern. So think about what that means now. Let's just say this is the distribution of bolts from my factory and the ultimate. I now know a lot about what to expect. I can expect most of my bolts. The highest probability of getting a bolt is right around my average. That's why we use the average a lot. If all we're caring about is where's the most likely place it's going to be, we use the average. Why? Because if it's normal, that's the highest probability. So we're going to have a lot of values around there. Now, as we move away from the average, the probability of getting a value decreases either way as we go up or go down. But there is still some probability that we can get values out here. That's why if we're interested in the min or the max, the probability distribution can tell us how far out we need to go before there's no chance that we can get a value out there. How do I know my boss isn't going to go to jail? I use the probability distribution and go out far enough. So you see the power of random variables, understanding they follow a distribution, and then we can use that to know what to expect. Okay, now let's stop here for a second because your head might be exploding because I'm talking about random variables, but yet predictability. It's like, whoa, those two words don't go together. If it's random, how can it be predictable? How can it look like that normal curve? So this next video is going to hopefully let you see how that happens. And you'll see I can't tell you the exact value of a random variable. They're random. But if I know the distribution, I can tell you the general pattern that values from that distribution from our factory will follow.
Right, so this is a Galton board because the first person to make one of these and name it after themselves was called Galton. And what you do is you take a ball, you drop it into the top, and it bounces off all these nails before eventually going into one of these categories. And when the ball hits each nail, in theory, there is a 50-50 chance of it going left or right. And so each path is pretty much unpredictable. If I was to take two balls and put them in, even if I try and put them in exactly the same, they will end up in completely different positions. We cannot accurately predict where any given ball will go. However, we can make a few statements. We can say that a ball is more likely to end up in the middle than the edge, because the center categories, there are lots of different paths that end up here. There are only a few paths that end up on the edge. So what we can do is take this piece of scientific equipment, attach it to the top, and start putting these in by the handful. If we put in absolutely loads of these balls, even though each individual one we couldn't accurately predict where it's going to end up, we can accurately predict the overall pattern from lots of them. Right, and that pattern we end up with is called the normal distribution. In fact, we've got a few too many in the middle there. Now, a lot of things in nature follow this pattern. If you measure people's height, they will follow a normal distribution. Shoe sizes, a lot of things in science and engineering and maths match this kind of bell-shaped curve. In fact, those of you, if you've done A-level maths, you will know that because the ball has choices of going left or right on each one, this is actually a binomial distribution. And if you have lots and lots of balls going down, as you get more and more of them, it gets closer and closer to exactly matching the normal distribution. So there you are. In probability, you can't predict the exact location one ball will end up, but you can say a lot about what will happen across many balls.
Okay, so hopefully that lets you visualize and see how a probability distribution, random variables follow predictable patterns. You can't predict one. And you can Google Galton board, and there's a lot of videos that show it happening, like they have some fancy ones that just flip over and over and over again, and they fall in that pattern. Why? Because the idea that he talked about, there's more paths that lead to the middle than the outside. So now imagine our factory. We've got raw material coming in. There's paths through the factory to make bolts. So imagine now the Galton board sitting over the top of that. There's a lot more paths that lead down the middle than there are to the side. Well, what do I mean by that? Well, we have all these machines, and there's variation in all the machines, but the machines are set to produce, on the average, a certain value. Well, most of the parts are going to be around that average on that machine. So we're going to have a lot more parts in here. But sometimes this machine wiggles this way, this one also wiggles that way, this one also wiggles that way, and lo and behold, we have a big one. Or the other thing happens. So you see, hopefully you can visualize how random variables going through the factory, the ultimate strength can end up looking like this. So we have the distribution of random variables is normal. We can't predict one, but there is a predictable pattern. And based upon that pattern, we can have an idea of what to expect because we can calculate probabilities of different things happening. Okay, now that's the normal distribution. Remember we said a distribution is described by shape, central tendency, and spread. Another shape is uniform. What does that mean? Well, if these are our numbers, this is the probability of those numbers happening. They all have the same probability. So what can I expect? I can expect anything by the same probability. I could expect an 81, an 85. Yeah, but the average is blah, blah, blah. Well, it doesn't matter because the distribution isn't around the average. Everything has the same probability of happening. Another distribution, which is used a lot, is the F, and there's a lot of different forms, but this one right here is a common one, especially with failure of electronic components. So imagine that down here is the time to failure. What is this saying? This is saying that if an electronic component is going to fail, the highest probability is right away, early on. As time goes on, the probability of it failing is lower and lower. Does that mean none will fail, after a certain amount of time? No. There's still a little bit of probability, but most of them are going to fail right there. So you see, there's different distributions for different kind of phenomenon. That's why I said you can't just always assume it's normal, but a lot of the things that we work with does follow the normal. Okay, so we're going to focus now on the normal probability distribution. We're going to assume for the time being that all the data that we're dealing with in the examples that I give is normally distributed. The data, the random variables follow a normal pattern. Okay, so back to our fundamental question now, we say, okay, we need to know what to expect. And we want to know what to expect from all possible samples, not just the ones we have. And we now have a way to do that. Because if the process, the population is stable, it's only varying by randomness, common cause variation. You're going to know what I mean in the last video when we start talking about real world things by that statement, but I wanted to get that up there. If it's stable, that means nothing's changing. The factory is just plugging along. Then the data that we take, those values are random variables. Random variables behave in a predictable manner, a predictable pattern described by the process generating them. And that population is described by a shape, a central tendency, and a spread. And for right now, we're going to assume the shape is normal. So here's what we're going to do. We have our factory. It's producing parts. If we measure the ultimate of those, that value, those values are random variables. There is a population, the factory. That is our population. It has some shape. We're going to assuming right now that shape is normal. It has some central tendency mu, and it has some spread sigma x. That exists. We don't know what it is, but it exists. What we're going to do is we're going to come and we're going to take samples from the factory. Looking at that sample to try to predict the behavior of the population is inferential statistics. So to do that, we can calculate the sample average and the sample standard deviation. And then what we can do with those is use them to estimate the population parameters. Use them to estimate these right here. With estimates of the population parameters, then statistics, the distribution, can tell me exactly what to expect from my factory for all possible samples. We can calculate those probabilities. So for example, let's say the minimum of my bolt, the standard, was 78.58, and we had average and standard deviation. What's the chance of making below the standard? I could come down here onto my normal distribution. I could use my average. I could use my standard deviation to estimate mu, to estimate sigma x, and I could say, okay, what's the probability of getting less than 78.58? And it could easily give it to me. Do you see that power of statistics? We now have a way to know what to expect from our population when we can't have all the data by only looking at a sample. Now, obviously, we're going to learn, we have to make sure it's a good sample. We have to make sure that these sample standard and averages, standard deviation, are good estimates for the population. And then statistics can answer that question and help us know what to expect. That original question we have, what can I expect out of you? This is the process that we can follow in order to be able to answer that question. Okay, so then in the next video, we're going to look at understanding the average and the standard deviation with normal data, because that's going to be then the foundation to use to calculate these probabilities and know what to expect.